Okay, so what we're going to talk about now, this is kind of a continuation of what we talked about last class. We were talking about how if you wanted to get from here in New Jersey to New York City, a few of you had some ways to go. You know, take this road, take that road, take the train. And we probably, of all the algorithms, the ways to get there, you probably were trying to find the one that's the most efficient. And your definition of efficient was probably the one that would get us there in the shortest amount of time. Unless you wanted to have the shortest amount of tolls or less miles, maybe less miles means less gas. So what we're going to be doing in our course is we're going to be talking about the efficiency of algorithms based on how much time they take to run, but the time is going to be compared to the size of the input. So we're going to have to somehow come up with a formula that says for this size input, your algorithm takes this much time. And then that's going to be our statement whether it's a good algorithm or not. So what I thought we'd do is, since we're going to be talking about, probably next class, different algorithms for sorting, I thought we'd go over maybe one algorithm for sorting. So first I'll describe how the algorithm works, then we'll look at the code, and then we'll try to count up how much time it would take to run. So this is an algorithm for sorting an array. Let's say you have a random array that has the numbers 22, 15, 37, 6, and 25. And your goal is to get the array into sorted order. So we're going to see many sorting algorithms, and this is one that's kind of intuitive. So what we basically do is we look at the first element, 22. We copy it into a field called key. So we save it there. And then we say for everything to the left of 22, we assume everything to the left of 22 is already sorted. And our goal is to put this number into its correct spot in that sorted list. Now right now there's nothing next to 22, so we're done. So the number 22 is sorted, and I kind of use green to mark it now that it's sorted. Okay, we go to the next step of our loop, and we go to the second field, 15. 15 can now assume that everything to the left of it has been sorted. And now all we want to do is put 15 into its correct spot. So we take 15, we write it into our key space, hold it for a second, because that's the field we're going to put in its correct spot. And then we ask ourselves, is 15 less than 22? And if so, we'll copy 22 up to this one. We don't really need to erase this 22 yet, but it obviously no longer belongs there. And then we go to the next spot, which doesn't exist. So now 15 we've got to put in this spot. So we copy this 15 over to here. And then we would consider this part of the array sorted. So now in the next stage of the algorithm, we have 15 and 22 are sorted, and we're trying to figure out where 37 goes. So we put 37 into our key field, and then we say to ourselves, is 37 less than 22? And if it's not, then we're done. We could put 37 in this spot, which is really where it was. And then we can consider these three fields sorted. So at the next iteration of our algorithm, we have 15, 22, and 37 are sorted. And we're now trying to put 6 in this array in its correct spot. So we copy 6 into the key field, and then we compare 6 to 37, and if 37 is more than 6, we copy 37 up one level. And then we go to the next one. So we have an index that's going down, while another index is going up. So 22 is less than 6, so it gets copied up to this field. And then we go to 15, and 15 is less than 6, so 15 gets copied up to here. And then this is like kind of, it's implied that maybe it's negative infinity. You know, everything is bigger than when you hit the end. So then we put 6 in our first spot, and now these 4 boxes are considered sorted. And then we do the last thing for 25. Take 25, copy it into our temporary holdings location, ask ourselves, is it less than 37? If so, we move 37 up. Ask if it's less than 22. It's not, so we put 25 right in this spot, and we're done. And erase sort. So that seemed like kind of an intuitive way of, you know, just you're trying to figure out a way to sort. You basically go through each element and put it in its correct spot, assuming everything up to that element has been sorted already. And just do them one at a time. So if we were to look at code for this, algorithm. This is an algorithm called insertion sort. So we'll probably learn about, I don't know, 6 or 7 sorting algorithms by name in the next couple of weeks, and this will be one of them. So this is called insertion sort. So basically you're taking an array, and then you're running from j equals 1 to the length of the array minus 1. We're copying the value into our key field. This is just a comment. But now we're going to sort, we're going to insert into the array. We're going to insert this new element into all the fields to the left of it. So the way we'll do that is we'll start an index 1 less than it, and then just walk all the way back to the beginning, finding the spot it belongs to. And this is the while loop that just walks back to the beginning. And we keep copying values over, decrementing the index I as we walk to the beginning until we find the spot where it belongs, and then we copy the field in. Right? So does this look like the code for the algorithm we just did? Okay, so now our question is, if you ran this algorithm on an array, you know, you type in, you hit enter to run, and you look at your watch, and you say, how long did it take? Well, hopefully, if n is small, you wouldn't be able to pick it up off your watch. Hopefully it'd be milliseconds. But if n was very large, it could take a long time. So the question is, how can we calculate how much time it takes? Your algorithm. Well, each of these lines compiles into some kind of, you know, machine code, and those instructions take a fixed amount of time. So if what we could do is, we could take every line of this code, if we knew, now this would be based on how fast your processor is, but if we knew how long each instruction took, and then we counted how many times does each instruction run, add the whole thing up, and that'll tell us how long the time is, right? Does that make sense? So we're going to say, we don't know, it depends on the processor. Like if whatever processor we're using today, 3 years from now might be 5 times faster. So we're just going to say that there's a cost, cost 1, cost 2 for each line. That's going to depend on how fast our processor is. What we're going to focus on is how many times does each line run. So for example, how many times would this line run? How many times do we take an element and copy it into our key area? I don't know why the author of this book called it a key. It should have been called temp, but they call it a key. So we copied it into our temp area. How many times would we do that for this algorithm? N. Right? Yeah, so in this case it would be 5 elements, but if we do 10, it would happen 10 times. So depending on the size of the input, it's done exactly 1 time for the entire running of the algorithm. Okay, so now, let's see, what else? So this line, this line will run, well, our book says n-1 because the very first time, we could have wrote the code a little bit more efficient. The very first element is already sorted. You know, the 22 just started off sorted, so we didn't have to copy it over and then copy it back. So with a little more efficiency, we could have done it n-1 times. Okay, and then this, how many times do we have the element we're looking at, do we have to have the pointer next to it and then start walking backwards? This would also happen n-1 times. Okay, so we can count exactly how many times this line, this is a comment, so it's going to run, but comments take no time. But this one we can count exactly how many times it's going to run. Now this inner while loop, the inner while loop is this. The inner while loop says, let's say for example, we're looking at the number 37. We write 37 over here, and then we put a pointer to the one next to it, and we start walking backwards until we find a number that's less than 37, and we stop. So how many times are we going to do that? So for example, with 6, we had to go 37, 22, 15. We had to go through the whole array. But when we were using 37, we only had to go once. So how many times will we run this code? how many iterations of this while loop will there be? Anyone, like, can you say concretely how many times it would run, or can you give a range? Well, okay, so I just want to make sure we get this, because this is kind of an important part, because this is where we're going to start talking about like the best case, the worst case, and an average case. Because it's not like every line runs exactly the same number of times. It's going to depend on the input. So when we get to the point where we're looking at the number 6, to get it into its correct spot, we had to go, actually had to go move this one up, move this one up, and move this one up. We had to do 3 operations. But when we had to put 37 into its correct spot, immediately, as soon as we started, it was in its correct spot. So we got to wait cheap on that one. So how many times are we going to have to push a number up each time that loop runs? How many times would we have to push a number up?
N times?
Is it always n times? Or is it?
N minus 1 times.
Okay, but is it always n minus 1? Like, the new number we get, does it always go to the very beginning?
No. No.
Like, it goes where? Like, so, I don't know, somewhere, but maybe at the beginning, maybe at the end, maybe in the middle. We don't know. And if the numbers are given to us, depending on how the numbers are originally given to us, it may take a long time or less time. So it's going to be n minus 1 times, because that's how much the outer loop runs. But then on each iteration inside here, it's going to be like some kind of random number. So we're going to use this number t to just be like some random number between 1 and n minus 1. However far you have to go until it finishes. But this number t is proportional to n. So it's going to be something like, on average, it's going to be half of n, or half of n minus 1. And then the bottom line, where the key gets copied into its correct spot, we also know that's going to run exactly n minus 1 times. Okay, so we have a line that's going to run, this outer loop has to run for all n, because it even has to do the test when you go outside of the array. So that's going to run 1 extra time. So we know this line's going to run n times, this line's going to run n minus 1 times, this line's going to run n minus 1, well, that's a comment. This line's going to run n minus 1. This while loop, so it's a while loop that's running inside of a for loop. So this loop is going to run n minus 1 times, and then each of those runs could run up to maybe on average half of n, so some relationship to n too. So if we wanted to calculate how many times, what's the total time of the algorithm? Oh, okay, so first of all, let's talk about what would be the best case scenario. If you could choose how the numbers are given to you, what would make this algorithm run quickly? Well, what would make the algorithm run quickly would be, the way this algorithm would run quick is, so the question is, what is the best case input you could get? Every time we take a number, like 6, and we want to put it in its correct spot, we have to keep looking here and go all the way to the beginning. What would make that happen as infrequently as possible? If the numbers came to us in what order originally? If they were already sorted. Because if they were already sorted, like let's say it started out like this. Well, we'd take 6, put 6 in the key, and then say, oh, 6 is in its right spot. Then we'd say, okay, 15, we'd put 15 in the key, and then go, oh, 15's in its right spot. So we wouldn't have to do that inner while loop. We'd only have to do it one time, and then we'd say we're done. So the best case scenario is when the numbers are already sorted. And if the numbers were already sorted, the algorithm would take line 1, 2, I didn't write line 3 because it's a comment. So it's the time it takes to do line 1, line 2, line 3, line 4, line 1, 2, 4, 5, and 8 are done n times. And then line 2, 4, 5, and 8 are done one additional time. Now, that would be if we're really lucky, so we can't count on being lucky. The numbers come to us already sorted. What's the worst case scenario for this algorithm? The worst case scenario would be every time we look at a new number, it goes all the way to the beginning. So how would the numbers be given to us so that every time we look at a new number, it has to go all the way to the beginning? If it was reverse sorted. So if the numbers happen to be given to us, because this algorithm assumes you get a random array, but if they happen to be given to us in the order of, 37, 25, 22, 15, and 6, then this is that outer loop is going to run exactly n minus 1 times n minus 1. That would be a worst case scenario. And what would be the average case scenario? And we'll cover more of this best case, worst case, and average case next class. But what would be on average? Like, what would we typically expect to happen? The numbers would come into us maybe every time you look at a number, it goes halfway through the array and then finds its final spot. So what would that be? Somehow the numbers would be scrambled up so that on average, its correct and final spot is halfway through the array. Okay, so in the worst case scenario, which is also extremely rare, but can still happen, so this is unfortunate, Apple takes n squared and makes them these arrow things, but anyway, so that's supposed to be n squared. So the while loop runs the line C5, the line that caused C5, C6, and C7 run, actually, the worst case scenario is if they're in the reverse order. And so what we're doing then is we're saying that we're taking each loop is run. Actually, this could also be considered on an average case. But the thing is, the while loop inside the for loop is run n times, the outer loop is running n times, and the inner loop is running n minus 1 times. So that ends up being, this should be like, n squared. So the amount of time the algorithm would take is lines 5, 6, and 7 are running multiplied by whatever your input number is squared, n squared, not n. And then lines 1, 2, 4, plus 5, 6, 7, and 8 over 2 run run n times. And then we've overcounted one of these by 1, so just for accounting reasons, we subtract off 2, 4, 5, and 8. So the running time of your algorithm, in the worst case, and it'll also end up being in the average case, is whatever n is, whatever the size of your input, it'll look like, now all I'm doing is taking all these constants and turning them into a letter A. I'm taking all of these constants. And again, these constants would just be how long those lines of code take to run on your particular machine. If you took this code and ran it on a slower machine, these numbers would get bigger. If you put it on a faster machine, they get smaller. But one thing is for sure, it'll always be the same number as long as you stay on that machine. So the running time of this algorithm has the form of some constant times n squared plus a different constant times n, and then plus a third constant. And that third constant in this case is a negative number. So it takes on this form. This is how long the algorithm would take. Okay, so suppose, I'm just going to make up some numbers. Suppose we have an algorithm that has a running time of a to the n squared plus b to the n plus c. And these constants come from how long your processor takes to run the instruction as part of, as far as when it compiles and runs those instructions on your machine. So suppose, for example, A was 15 nanoseconds. That's 10 to the minus 6 seconds. Let's say we could do that. And then this B part, which could be, 6 or 7 lines in your code running on your particular machine. If we added it all up, let's call that B, some constant B. Let's say that takes 35 nanoseconds. And then the third set of constants added together takes 25 nanoseconds, right? So here's what we're doing. I just don't want you to lose sight of this. We're looking at an algorithm. We're taking how long each line takes to run. Right, so here's what we're doing. We're taking each line of your C or Java code, maybe compiles into 3 or 4 machine instructions, that really doesn't matter here. Each line of your Java code takes a certain amount of time to run. Now what we're doing is we're looking at your algorithm and saying if we ran your algorithm, how many times does each line run? And we start to realize it's proportional to the size of the input, n. If the input gets bigger, these lines run more often. So we're going to calculate how much time each line takes to run, how many times does it run, multiply all those together, add the whole thing up, and that's how much time your algorithm takes. So we take, that's what these costs are. Then we start to find as loops are running inside of loops that the numbers get factored together and end up being in an equation something like this. This is a pretty big equation, so then we just take the cost of line 5, the cost of line 6, the cost of line 7, divide it by 2, and we'll multiply that by n squared, and then put all these numbers together and just get numbers of this form. So really all A is, in this equation, is C5 plus C6 plus C7 divided by 2. That's A. I've just summed it up into one new number. So when I say, like, let's say A is 15 nanoseconds, that means the time it takes to run line 5, line 6, line 7 divided by 2 comes out to 15 nanoseconds. Okay, so suppose we had an algorithm. You calculated how much time it takes to run, and you picked one of the cases, best case, worst case, average case. So we were able to say that it has, let's say all those constants added up make an A of 15 nanoseconds, B of 35 nanoseconds, and C of 25 nanoseconds. So if n was equal to 1, how long would the algorithm take to run? Well, it would be 1 times 15 plus 1 times 35 plus 25, which would add up to 75 nanoseconds, right? If we ran your algorithm on an array of size 1, it's kind of pointless to sort an array of size 1. It's already sorted, right, as soon as it starts. But if we did that, your algorithm would take 75 nanoseconds. This part of your algorithm takes up, so I basically just did this in Excel. I just said what percent is this number of this number. So 20% of your algorithm is done here. 46% of your algorithm is done here, and 33% of your algorithm is done here. Hopefully that adds up to 100. Yeah. Okay, now, does anything change as the array gets bigger? Well, let's run the same algorithm, but an array of size 10. Okay, so the part that takes 15 nanoseconds gets multiplied by 10 squared, gets multiplied by 100, and it becomes 1,500 nanoseconds is how long this part will take when n equals 10. When n equals 10, this part, this 35, gets multiplied by 10, so we lose a decimal place. And this part is unaffected by n. No matter what n is, this last part it was all the instructions that ran only one time. So the algorithm would take this number plus this number plus this number. Now the algorithm takes 0.001875 nanoseconds. And then if we took the percentage of time we spend here, 80% of our algorithm is spent doing this code. This is mostly that inner while loop is now taking up 80% of the algorithm. So what I want to get across is as n gets bigger, there's certain parts of our algorithm that are going to take up much, much more time than the other parts. So we get to n equals 100. So we take 15 nanoseconds and multiply it by 100 times 100, which would be 10,000, right? So we take this and multiply it by 10,000. And we're going to take the second part, multiply this by 100. So 35 nanoseconds now becomes 35 nanoseconds times 100. So we lose 2 decimal places. And this again stays the same. The total time of our algorithm is, now it's almost, 1/7 of a second. So now it's like starting to take up a little time. It's not going to be done in the flash of an eye. If you're trying to sort 100 numbers, it'll still be done. As soon as you hit enter, the result will be done. But at this point, with n equal to 100, 97% of the time it takes to run your algorithm is being run in this section. That's that inner while loop. 97% of your algorithm is. So this code, when you run this algorithm on an array of size 100, we grab a number, we put it in the key field, and then we go all the way back looking for its correct spot. On average, we're going to be going back like 50 squares, and then putting it in its correct spot. Then we go to the next step, and we take another one, we start walking back to the beginning. So at the point where n equals 100, your algorithm is spending 97.7% of its time in that while loop. And then let's say n goes to 1,000. So if n is at 1,000, then it's 15 nanoseconds times 1,000 squared, which would be 1,000 with 6 zeros. That would make, we'd be spending 15 seconds inside that while loop. And then we take b, which is 35 nanoseconds, multiply that by 1,000. So we're going to spend 0.035 seconds in the for loop section. And then we're still going to spend 0.00025 seconds on the steps that only run one time per algorithm. So when n equals 1,000, you're going to spend 99.77% of your time inside that while loop. 0.020, less than one-fifth of, or 1/4 of 1% is spent in the for loop. And this, I use Excel with 2 decimal places after the percent and round it off to 0. 0% of the time is those instructions that get run once. So looking at something like this, what would be the phrase you would use to say, like, how good is this algorithm? So in other words, like, if you're asked to give an algorithm like, how to drive from here to New York City, you would say, well, it's a good algorithm because it takes, an hour and a half to get there, and I can't think of any better way to do it. But how would you describe this algorithm? Like, where's all the cost going? So when n is very small, the cost is kind of spread around on all the steps. But when n gets very large, all the cost is in that inner while loop. Cool. What'd you say? You have any?
I want to say efficient, but that's not.
Well, no, I mean, if, as n grows large, as n starts getting large, what would we focus on to talk about how efficient the algorithm is? Like, would we focus on this part, this part, this part, a combination of the two? Does one part seem to totally dominate the algorithm as the algorithm gets, as n gets very, very large? Yeah, so we kind of want to make a statement that says something to the effect of, so yeah, what you're saying is the n squared part is, when n gets large, that part takes over. N is small, all the parts matter. But when n gets very large, if somehow we could do that part better, that would be a big savings to us. So we want to say something like, as n gets very large, this part is dominating the whole algorithm. We want to somehow make a statement like that. So if you come up with an algorithm that has 3 parts to it, and one has an n squared component, and someone else comes up with an algorithm that has 3 parts to it, but there is no n squared, maybe there's an n or something halfway between n and n squared, we'll do n log n later on. That might be much better because the dominating part will be smaller. So we want to somehow tie this algorithm, we want to come up with a bookkeeping method where we can tie this algorithm to the idea that this part is, when n becomes very, very large, this part is going to dominate all the time we spend on it. We want to make a statement that says something like, this algorithm is tied to the concept of n squared times some constant. The constant being however long line 5, 6, and 7 take. Then you're multiplying that small number, some small nanoseconds, by n squared, and when n becomes very, very large, this will dominate the whole algorithm. 98, 99% of your time is spent right here. And this other stuff really doesn't matter too much. So we want to make a statement like that. So what would, if you were trying to, so in the analysis of this algorithm, we made an observation that when n gets very, very large, 99% of the time is spent in that n squared part of the algorithm. So what would your statement be? How would you make that statement? That when n becomes very large, this part dominates the algorithm. Is there a way to make that, how would you phrase that? Any ideas? Like I said, we have three components. The running time of your algorithm, let's say this was a function t. Let's say t of n. You give input in n, and then it gives you a function that tells you exactly how much time the algorithm takes. And then you ask the question, if you ask the question, how much time does it take, you'd have to give the whole function. But if you wanted to make a statement that when n gets very large, only one part matters, how would you make that statement? So it's the part where it has the n squared part to it, not the multiplied by n or just the constant by itself. So is there just any way you'd think of making a statement that you say, this algorithm is dominated by the n squared part? Something like that. Meaning as the algorithm gets very, very, as n gets very, very large, that's the dominating part. Okay, so, all right. So there's a notation, and we can pick this up next class. But it's a little bit tricky when you're first learning it. But the idea is, and yeah, we can cover this next class. Maybe what I'll do is I'll just go over the definition of them now, and then we'll go into more details later on. But suppose you had a function, f of n, and you wanted to make a statement that it is dominated by some other function, like our n squared function. You know, in other words, this function is a n squared plus b plus c, and we want to make the statement that it's being dominated by a function that has an n squared flavor to it. That's the statement we want to make. And what we're saying by that is that as n becomes very, very large, the biggest component of this thing is this part. So we want to make a statement something like that. And I'll go over a more clear, and we can go over examples too, next class. But we're going to make a statement that goes like this. Suppose you have a function, f of n, and so, for example, this f of n could be a n squared plus bn plus c. If we could find a constant c and a particular starting number n0 and make the statement that from n0 going on forward, this statement will always be true, then what we would show is that there's a term in here, like the n squared component, would be always less than some other constant times a function that would also have an n squared component. So then we're basically going to make this statement. Like I said, we'll pick up next class on these definitions, and we'll go over examples of them and what they mean, but I just wanted to cover why we're doing this. So basically, we're saying a function is, we'll use the letter big O, we'll say it's big O g of n if there's a function f of n which is dominated by g of n. Omega would be the opposite side, that it would be the least component, so this would almost equate to the best case scenario of our algorithm. And then if you happen to come up with a function that does both, we can combine this. This is theta. It's going to be, if both of these are true, then theta would be true. So yeah, like I say, I'm going to go over, next class, we're going to talk about big O notation and then theta and omega. Next class. But I just wanted to go over just, the idea that what we're doing here is taking an algorithm, taking how long each line takes to run, count up how many times each one will run, add the whole thing up and come up with this long time function, and then somehow come up with a statement that says this algorithm is good or not good based on its dominating terms as n becomes very, very large. Okay, yeah, so we'll pick up, I guess, on this slide next class. Would anyone have any question up to this point?